All right, today we're jumping into a topic that's really at the heart of all statistics, something that shows up everywhere from a simple coin toss to the crazy world of the stock market. We're talking about probability. It's basically the language we use to talk about uncertainty. So let's get right to it.
So let's start with something we all know. Heads or tails. If you flip a coin, what are the odds it lands on heads? You'd probably say 50-50, right? And yeah, you're not wrong, but why are you right? Getting to the bottom of that why is really the first big step in understanding how probability actually works.
Okay, so here's the official definition from your stats class. Probability is the long-term relative frequency. Now, that sounds a little academic, I know, but the idea behind it is actually pretty simple. See, probability isn't about predicting what happens on one single coin flip. No way. It's all about the pattern you see when you do it over and over and over again, like thousands of times.
For instance, let's say you flip a coin just 10 times. You could totally get 7 heads. That's 70%. Now, if you stopped right there, you might think, hey, this coin is rigged. But this is a perfect example of how, in the short run, random chance can look really lumpy and weird. This one little experiment doesn't tell you the real story.
Okay, but what happens if we do more? Let's bump it up to 100 flips. Now, maybe we get something like 53 heads. See that? 53%. We're already getting way closer to that 50-50 mark that we all expect. The more you do it, the more all that random short-term luck just kind of cancels itself out.
And this right here is the law of large numbers in action. After, say, 10,000 flips, I guarantee you the percentage of heads is going to be almost exactly 50%. This isn't just some abstract idea. It's literally how casinos build their business and how insurance companies know they're going to be profitable. Over the long haul, things always settle back to their true probability.
So if probability is this big, powerful thing, it's got to have some rules, right? You bet it does. Before we can start calculating stuff, we need to know the 2 golden rules, the absolute boundaries of chance. Rule number 1 is the range rule. And honestly, it's super simple. It just says that any probability has to be a number between 0 and 1. That's it. A 0 means it's an impossible event, like there's no way you're rolling a 7 on a normal 6-sided die. A 1 means it's a certain event. You are definitely going to roll a number between 1 and 6. Everything else, every other probability, just lives somewhere on that line between impossible and certain.
And golden rule number 2 is the sum rule. This one's just as critical. It says if you figure out every single possible thing that could happen, no exceptions, and you add up all of their probabilities, that total has to equal exactly 1, because you've covered 100% of what could possibly happen.
Just look at this table. It makes the sum rule totally clear. With a regular die, you've got 6 possible outcomes. As you can see, each one has a 1 in 6 chance. So what happens when you add 1/6 plus 1/6 6 times? You get 6/6, which is just 1. See? All possibilities are accounted for.
Okay, we've got the rules down. Now we need the tools of the trade. To actually start calculating probabilities, we need to get comfortable with 2 key building blocks, the sample space and the event.
First up is the sample space. We usually just call it S. Think of this as your complete map of possibilities. It is a full list of every single unique thing that can happen in your experiment. Figuring out your sample space is always step 1.
Let's go back to our trusty die roll. What's on the map? Well, you can roll a 1, a 2, a 3, a 4, a 5, or a 6. That's it. That little set of 6 numbers, that's your entire sample space. All right, so if the sample space is the whole map, then the event, which we call E, is the treasure you're looking for. It's the specific thing or group of things you actually want to measure. It's always going to be a smaller piece taken from that bigger map. So let's say we're hunting for the event rolling an even number. What's our treasure? We'll just look at our map, our sample space, and pull out everything that fits the bill. In this case, that's the 2, the 4, and the 6. That little set is our event.
So now that we have these 2 pieces, the event and the sample space, we can finally put them together with the classical probability formula. This thing is simple but so powerful as long as every outcome has an equal chance. It's just the number of ways your event can happen divided by the total number of things that could happen.
So let's plug in our numbers from the die roll. The number of ways our event, rolling an even number, can happen is 3, right? 2, 4, 6. And the total number of outcomes on our map is 6. So you just do 3 divided by 6, which is 0.5, or a 50% chance. It really is that straightforward.
Okay, let's bring it all home. We've got the rules, we've got the building blocks. Now we're going to put it all together to build something you'll use all the time in stats, a complete probability model.
So what is a probability model? It's really just the complete blueprint for your experiment. It's a neat and tidy list that shows every single outcome side by side with its exact probability. You know that die roll table we looked at earlier? That was a perfect probability model.
And here's a fantastic little pro tip for checking your own work. How do you know if your model is actually correct? Well, you use our 2 golden rules as a quick 2-step test. Step 1 is every single probability you listed somewhere between 0 and 1. Step 2, do they all add up perfectly to 1? If you can say yes to both, you're golden. Your model is valid.
Before we wrap this up, I want to leave you with one of the most useful things you can do with all this, a concept that's going to pop up again and again in any statistics course, and that's the idea of an unusual event.
In the world of stats, we have a specific agreed-upon cutoff. A magic number, really. We officially call an event unusual if the probability of it happening just by random chance is less than 5%, or 0.05. This number is huge. It's the foundation for figuring out if a scientific result is a real discovery or if it was just a random fluke.
And there you have it. That's our introduction to the basic rules of chance. We've talked about how patterns emerge over the long run, we've learned the 2 golden rules that keep everything in line, and we even build a probability model from the ground up. So I'll leave you with a question to chew on. Using that 5% rule as a guide, what's the most statistically unusual thing that's ever happened to you? Thanks for tuning in to this explainer.